The chemistry of the global climate. We live in a greenhouse. Life on Earth depends on energy coming from the sun. About half the light reaching Earth's atmosphere passes through the air and clouds to the surface, where it is absorbed and then radiated upward in the form of infrared heat. About 90% of this heat is then absorbed by the greenhouse gases and radiated back toward the surface, which is warmed to a life-supporting average of 59 degrees Fahrenheit, 15 degrees Celsius. Here you can see the Earth radiation balance. The incoming solar radiation is absorbed by water, clouds, and surface and reflected as outgoing radiation. The infrared radiation by surface is absorbed and emitted by atmospheric gases, water vapor, and dust. A layer of greenhouse gases, primarily water vapor, and including much smaller amounts of carbon dioxide, methane, and nitrous oxide, acts as a thermal blanket for the Earth, absorbing heat and warming the surface to a life-supporting average of 59 degrees Fahrenheit, 15 degrees Celsius. Most climate scientists agree the main cause of the current global warming trend is human expansion of the greenhouse effect, one warming that results when the atmosphere traps heat radiating from Earth toward space. Certain gases in the atmosphere block heat from escaping. Long-lived gases that remain semi-permanently in the atmosphere and do not respond physically or chemically to changes in temperature are described as forcing climate change. Gases, such as water vapor, which respond physically or chemically to changes in temperature, are seen as feedbacks. Gases that contribute to the greenhouse effect include water vapor, nitrous oxide, methane, carbon dioxide, sulfur hexafluoride, and chlorofluorocarbons. Water vapor. The most abundant greenhouse gas, but importantly, it acts as a feedback to the climate. Water vapor increases as the Earth's atmosphere warms, but so does the possibility of clouds and precipitation, making these some of the most important feedback mechanisms to the greenhouse effect. Carbon dioxide, CO2. A minor but very important component of the atmosphere, carbon dioxide is released through natural processes such as respiration and volcano eruptions, and through human activities such as deforestation, land use changes, and burning fossil fuels. Humans have increased atmospheric CO2 concentration by a third since the Industrial Revolution began. This is the most important long-lived forcing of climate change. Methane. A hydrocarbon gas produced both through natural sources and human activities, including the decomposition of wastes in landfills, agriculture, and especially rice cultivation, as well as ruminant digestion and manure management associated with domestic livestock. On a molecule-for-molecule basis, methane is a far more active greenhouse gas than carbon dioxide, but also one which is much less abundant in the atmosphere. Nitrous oxide. A powerful greenhouse gas produced by soil cultivation practices, especially the use of commercial and organic fertilizers, fossil fuel combustion, nitric acid production, and biomass burning. Chlorofluorocarbons, CFCs. Synthetic compounds entirely of industrial origin used in a number of applications, but now largely regulated in production and released to the atmosphere by international agreement for their ability to contribute to destruction of the ozone layer. They are also greenhouse gases. Sulfur hexafluoride, SF6, is the most potent greenhouse gas that it has evaluated, with a global warming potential of 23,900 times that of CO2 when compared over a 100-year period. Sulfur hexafluoride is also extremely long-lived, is inert in the troposphere and stratosphere, and has an estimated atmospheric lifetime of 830–200 years. Water vapor is known to be Earth's most abundant greenhouse gas, but the extent of its contribution to global warming has been debated. Using recent NASA satellite data, researchers have estimated more precisely than ever the heat-trapping effect of water in the air, validating the role of the gas as a critical component of climate change. The contribution of each gas to the greenhouse effect is affected by the characteristics of that gas, its abundance, and any indirect effects it may cause. For example, the direct radiative effect of a mass of methane is about 72 times stronger than the same mass of carbon dioxide over a 20-year time frame, but it is present in much smaller concentrations so that its total direct radiative effect is smaller, in part due to its shorter atmospheric lifetime. On the other hand, in addition to its direct radiative impact, methane has a large, indirect radiative effect because it contributes to ozone formation. Global warming potential, GWP, is a relative measure of how much heat a greenhouse gas traps in the atmosphere. It compares the amount of heat trapped by a certain mass of the gas in question to the amount heat trapped by a similar mass of carbon dioxide, whose GWP is standardized to 1. CO2 is the most emitted gas and the best studied. Therefore, it was defined as a standard for definition of global warming potential of the greenhouse gases. On Earth, human activities are changing the natural greenhouse. Over the last century, the burning of fossil fuels like coal and oil has increased the concentration of atmospheric carbon dioxide, CO2. This happens because the coal or oil burning process combines carbon with oxygen in the air to make CO2. To a lesser extent, the clearing of land for agriculture, industry, and other human activities have increased concentrations of greenhouse gases. Here you can observe the trends of the major greenhouse gases: carbon dioxide, nitrous oxide, methane, and chlorofluorocarbons, hydrochlorofluorocarbons and hydrofluorocarbons. You can see that the amount has increased exponentially since the Industrial Revolution, and the contribution of CO2 is very important. 3 times the methane and 10 times the nitrous oxide. Concentrations of the main greenhouse gases have increased over the past 6 years. Thus, during the maximum concentration for CO2 it was 300 parts per million and has reached nearly 403 ppm. Methane has risen from 800 parts per billion to 1,875 parts per billion, and nitrogen oxide 300 parts per billion to nearly 330 parts per billion. These are extreme increases. The planet Mars has a very thin atmosphere, nearly all carbon dioxide. Because of the low atmospheric pressure, and with little to no methane or water vapor to reinforce the weak greenhouse effect, Mars has a largely frozen surface that shows no evidence of life. The atmosphere of Venus, like Mars, is nearly all carbon dioxide. But Venus has about 300 times as much carbon dioxide in its atmosphere as Earth and Mars do, producing a runaway greenhouse effect and a surface temperature hot enough to melt lead. The consequences of changing the natural atmospheric greenhouse are difficult to predict, but certain effects seem likely. On average, Earth will become warmer. Some regions may welcome warmer temperatures, but others may not. Warmer conditions will probably lead to more evaporation and precipitation overall, but individual regions will vary, some becoming wetter and others drier. A stronger greenhouse effect will warm the oceans and partially melt glaciers and other ice, increasing sea level. Ocean water also will expand if it warms, contributing further to sea level rise. Meanwhile, some crops and other plants may respond favorably to increased atmospheric CO2, growing more vigorously and using water more efficiently. At the same time, higher temperatures and shifting climate patterns may change the areas where crops grow best and affect the makeup of natural plant communities. In its 4th assessment report, the Intergovernmental Panel on Climate Change, a group of 1,300 independent scientific experts from countries all over the world under the auspices of the United Nations, concluded there's a more than 90% probability that human activities over the past 50 years have warmed our planet. The industrial activities that our modern civilization depends upon have raised atmospheric carbon dioxide levels from 280 parts per million to 400 parts per million in the last 150 years. The panel also concluded there's a better than 90% probability that human-produced greenhouse gases such as carbon dioxide, methane, and nitrous oxide have caused much of the observed increase in Earth's temperatures over the past 50 years. They said the rate of increase in global warming due to these gases is very likely to be unprecedented within the past 10,000 years or more. The panel's full summary for policymakers' report is online. It's reasonable to assume that changes in the sun's energy output would cause the climate to change, since the sun is the fundamental source of energy that drives our climate system. Indeed, studies show that solar variability has played a role in past climate changes. For example, a decrease in solar activity is thought to have triggered the Little Ice Age between approximately 1650 and 1850, when Greenland was largely cut off by ice from 1410 to the 1720s and glaciers advanced in the Alps. But several lines of evidence show that current global warming cannot be explained by changes in energy from the sun. Since 1750, the average amount of energy coming from the sun either remained constant or increased slightly. If the warming were caused by a more active sun, then scientists would expect to see warmer temperatures in all layers of the atmosphere. Instead, they have observed a cooling in the upper atmosphere, and a warming at the surface and in the lower parts of the atmosphere. That's because greenhouse gases are trapping heat in the lower atmosphere. Climate models that include solar irradiance changes can't reproduce the observed temperature trend over the past century or more without including a rise in greenhouse gases. Conference of the Parties COP, what's it all about? The international political response to climate change began at the Rio Earth Summit in 1992, where the Rio Convention included the adoption of the UN Framework on Climate Change, UNFCCC. This convention set out a framework for action aimed at stabilizing atmospheric concentrations of greenhouse gases, GHGs, to avoid dangerous anthropogenic interference with the climate system. In 1997, Kyoto Protocol decided upon 1. Emission reduction targets of greenhouse gases for each of the member countries. 2. A greenhouse gas emission trading program. 3. Holding future meetings to set penalties for violators of the established targets and regulation rules of the emission trading program. The Kyoto Protocol finally came into effect on February 16, 2005, 7 years after it was first negotiated, when the goal of getting countries responsible for a total of 55% of the global emissions was achieved with the signature of Russia ratifying the document. 2015 Paris Climate Conference. The Paris Agreement's central aim is to strengthen the global response to the threat of climate change by keeping a global temperature rise this century well below 2 degrees Celsius above pre-industrial levels and to pursue efforts to limit the temperature increase even further to 1.5 degrees Celsius. Additionally, the agreement aims to strengthen the ability of countries to deal with the impacts of climate change.